So hello everyone, welcome to this new session. So in our previous sessions we have discussed one concept called as mesh analysis, super mesh, and we have discussed a lot of problems related to those different kinds of circuit. Okay, so now we would be dealing with one more different kind of circuit, and that concept name here is node voltage analysis. Okay, first thing we have discussed about mesh analysis. Now this is the reverse process, that is node voltage analysis. In mesh analysis, what we did in mesh analysis, we used the Kirchhoff's voltage law, KVL. In this case, we are going to use the Kirchhoff's current law, that is KCL. Okay, that is all the average input currents in the output side. When it goes to output, it will be equal to 0. Okay, that is the KCL, Kirchhoff's current law. Okay. So now based on that Kirchhoff's current law, in this node voltage analysis, our goal is to find the voltages in this case. In the mesh analysis, using the loops, we had to find the loop currents, right? In this, our goal is to find the node voltages. Okay. In mesh analysis, we had loop currents. In this, we are solving for node voltages. Okay. So this was this brief concept about node voltage analysis. So in this concept, I am going to wind up this concept within 2 sessions, and I am not going to solve any problem because I already have the solved problems in my notes. That only I am going to explain it to you all. Okay. So because we don't have time, so around 4 to 5 problems I have in my notes, that I am going to explain it to you all. First, let us see what is this node voltage analysis with some of the examples. The current through the branch is the potential difference across it divided by the resistance of the branch. Okay, that is simple way they have given the statement as I is equal to V by R. Okay, that only they have just told it. That is the current through the branch I is the potential difference across it, that is V, divided by the resistance, that is by R. Okay, that is I is equal to V by R. So now consider the various cases here. That is, here we have one branch here. Between the two terminals we have one resistor, name it as R1. The two terminals, they have named it as VB and VC, and the current flowing through this terminal, they have named it as I1. So consider VB and VC. So use this condition, that is I1 current, that is equal to VB minus VC divided by R1, that is VB minus VC divided by R1. Okay. Similarly, for second, here we have I2 current, VB and VE, and here, but the value of VE, they have given it as 0 volts, so this is a ground voltage. Okay, that's why I2 is equal to VB by R2. That is, since the value of VE is 0, VB minus VE by R2, the value of VE is 0, so we would be getting VB by R2. So now consider VF consisting of source voltage V. Okay. That is, we have two terminals here, VB and VF, and between that we have one voltage source along with the series resistance. So in this case, the branch current I3, what is the value of that I3? Let us see. That is again very simple, VB minus V, because here also we should be starting from VB up to VF divided by the total resistance. Okay, in this case, start from VB and check the how many voltage sources are there, that all of them we should be subtracting. Not subtracting, if we start from here, the outward sign here is minus, right? So that's why we would be getting VB minus V minus VF. Okay, since the value of VF is 0 volts, so I have written 0 divided by the resistance R3. Okay, if this was minus plus, then this would be plus V. Okay, we should be checking the outward side. Similarly, if V is equal to 0, this is the equation here. They have substituted the value of V as 0. The next here is again. So here now in this case, they have just changed the polarity, as I have told you here. Again, they have done the same thing. So that is I4 current is equal to VB plus V minus V0 by R4. Like this, if we have the branches like this, and these points are represented as nodes. Okay. And in order to find the current through those branches of nodes, we should be finding using the condition I is equal to V by R, and from one node to second node we should be subtracting them and then divided by the resistance of that node. Okay, so these are some of the general examples. So then we have here KCL is required to write the node equations. Okay, in order to write the node equations, we should be using the KCL. I've told you already, that is the Kirchhoff's current law. So this is the definition of node. It is a point on network where 2 or more branches meet. Okay, that is called as node. It is a point on the network where two or more branches meet. Okay, for example, like this we have one network, then here we have one resistance, and here these three branches meet at this particular point, and that point is called as a node. So now what is this principal node? It is a point where three or more branches meet. Okay, so here I have explained this here in this case three or more branches meet, so that's why that node is called as a principal node. That is, we have an equation for principal node, that is number of nodal equations is equal to number of principal nodes minus 1. This is the condition which should be remaining the same for all the sums which you are solving for node voltage analysis. This you should be remembering, that is number of nodal equations, that is whatever the node equations we get, how much ever node equations we get, that would be one less than the principal nodes in the problem. Okay, that would be checking with one problem. Okay, the reference node or the datum node, the reference node is also called as the datum node, is node where the voltage is assumed to be 0. This is one definition of reference node. So these theory are clear about node analysis. So now let's discuss this node analysis with some of the problems. Okay, so here we have the first problem, that is in the circuit below use node analysis to determine the node voltages. Okay, so here we have one circuit here, but here we should not be applying the mesh analysis by writing the loops. Here we should be doing the node analysis, so we should be considering the nodes. Okay, I've told you the definition of node, that is two or more branches meet. So in this case, here we can consider this as one node where here three branches meet. This as one node, three branches meet. So these two nodes we can call it as two principal nodes. So now how to solve here is solution. Name these two nodes as any two values of these two nodes. Here in this case I have named it as VA and VB. Okay, and from this node we have three branches, right? Name those three. If we have three branches, we should be naming the three branch currents as well. Okay, starting from this node only, all three branches would be moving outwards. Okay, this direction, this direction, this direction for this node. Similarly for this node, it would be moving outwards. Okay, that is VA. We would be having three branch currents, since this principal node is the connecting three branches, so that's why name any three currents, I1, I2, I3 I have named in this case. Similarly for VB, I have named three branch currents as I4, I5 and I6. Okay, I4, I5, I6. Then these are some of the basics. Then we should be writing the node equation on node A using the Kirchhoff's current law. We know that Kirchhoff's current law is I1 plus I2 plus I3 equal to 0, right? This is the equation for Kirchhoff's current law, KCL. For all the problems, this we should be remembering. Then find the values of I1, I2, I3, because in this case node voltage analysis, I have told you, right, our goal is to find the voltages, that is node voltages VA and VB in this case, but we have the equation of current. So we know that I is equal to V by R. That relation we should be applying here for all the nodes. That is in this case equation on node A, that is this is the node VA here. In this we have three branch currents I1, I2, I3, that I have written it as I1 plus I2 plus I3 equal to 0. Then find the value of I1. I have told you, right, I1 is this branch here. You can see that this is the I1 branch, and from here till here this will be one single branch, and for that single branch you should be finding the value of current, which we have discussed with some of the examples. Like that only, let's try to find the value of I1 here. In this case it is V by R, that is VA, that is here in this case it is node voltage VA minus 25, because this is the outgoing sign here and we have one more voltage source, so that is minus 25 divided by the resistance 5. In this branch we have only one resistance, that is 5 ohm. Then I2 is equal to VA divided by 1, because we have here 1 ohm resistance, so that's why I have written it as I2 is equal to VA. Similarly I3 from here till here, okay, that is VA minus VB, because in this from here to here we have two voltage sources, right? One is VA and VB, so that's why VA minus VB divided by between this branch one resistance, that is 10 ohm, that you should be dividing. Like this we found the values of I1, I2, I3. Then substitute the values of I1, I2, I3 in this equation here. I have substituted here. Then nothing much to do, simplify. Okay. So in order to simplify here, like this we have the equation, right? try to write the voltage sources VA, VB and VC separately. Then the values with that the coefficient of that, try to represent it separately. So here in this case we have had VA by 5. So what I have done, VA into 1 by 5. Okay, in order to make you solve the problems easier, I have done it. Then minus 25 by 5 plus VA into 1 by 10 minus VB into 1 by 10 equal to 0. Then group all the VA terms. VA, we have 3 VAs, take common. Along with that we have 3 terms, 1 by 5. VA's coefficient is 1 and 1 by 10. Add them up. Minus VB into 1 by 10 is equal to 25 by 5 is minus 5. If you bring it to other side, it would be plus 5. Like this, we got one equations completely of all the voltages, right? Name it as equation 1. Similarly, apply KCL on node B, that is I4 plus I5 plus I6 is equal to 0, which I have seen in this circuit only. So here the value of I4 is VB minus VA divided by 10. The value of I5 is VB minus 0 divided by 2, that is VB by 2. And the value of I6 is VB minus 10 divided by 8. So let us check all the values. So yeah, the values are same. I have substituted the value of I4, I5, I6, solved it and grouped VA and VB terms together, and we have got this equation 2. So now we got these two equations. Put it in the calculator as it is, the coefficients of VA and VB, which I have already told you in mesh analysis how to do it. Okay, once again I am going to tell you only once now. Rest all the problems I am directly explaining. Only once I am telling you all how to do it. That is mode setup, 5 equation. Then we have only 2 voltages, so that's why press 1. Then write the coefficients. That is, in this case it is, write this full coefficient as it is. That is 1 by 5. Then we have plus 1 plus 1 by 10. Feed all the values, then press equal to. Automatically the answer would be feeded here. Okay. And similarly the next coefficient, that is minus 1 by 10. Since we have minus VB, minus 1 by 10. That is minus 0.1. It is feeded here. See. Then we have, here we have 5, plus 5, right? Okay, then next here we have minus 1 by 10 again. Then 1 by 10 plus 1 by 2 plus 1 by 8. Then we have 10 by 8. Like this you have stored all the values, press equal to. Here we will be getting 2 roots, 2 values of, first is value of VA 4.02. Next is value of VB 2.27. Like this we should be finding the node voltages. Okay, hope this is clear.